Reading the graph of f of x to find derivatives. Objectives. By the end of this lesson, you should be able to recognize graphically when a function fails to be differentiable at a point, approximate and analyze the derivative at x equals a given the graph of f of x, given a graph of f of x, sketch a graph of f prime of x, and explain the relationship between locally linear and differentiable. Before we look at a graph of f of x to determine what the graph of its derivative, f prime of x, would look like, we want to look at the types of non-differentiability on a graph. So a function is not differentiable at a few different types of locations on a graph. So the first two I want to look at are at cusps and at corners. So remember that a derivative is the slope of a tangent line. So at this place right here, at this x value a, I cannot find a unique tangent line, so I would want a line that first of all just grazes the curve. So maybe we might think that this one would work and goes through the point, but what about this line here? So there's not a unique tangent line at a cusp, and similarly at a corner. So right here, this line or this line, there's too many different options. So at a corner or at a curve, so here at 0 or here at this location a, the function fails to be differentiable. So we would call that a place of non-differentiability. And there are two more locations where a function can fail to be differentiable. The next one is at a vertical tangent line. So if you notice this graph here, at this location marked as C, if I were to draw a tangent line, one that just goes through that one point near the point C and just sort of grazes the function, that tangent line would be vertical. And a vertical line has an undefined slope. Well, if the derivative is the slope of the tangent line, I can't have it be a non-real number because remember that a derivative is a limit. So at a vertical tangent, I would also say that my function is non-differentiable. And then finally, at places of discontinuity. So if we remember, differentiability, so I'm going to abbreviate this, implies continuity. And wherever you're discontinuous, you are also non-differentiable. So at any place of discontinuity, and remember those are jump, removable, infinite, and oscillating discontinuities, I would also not be differentiable at that location. So those are all the different ways that I can fail to be a differentiable function. Alright, now we're going to take a look at a graphical interpretation of derivatives given the original function f of x. So we did this a little bit earlier. We analyzed some piecewise functions where each piece was, for the most part, linear. And the derivative of a linear function is just the slope of the line. But we're mostly going to deal with curves. So let's take a look at this curve and consider it to be the original function f of x. So let's say this is the curve f of x here. And we want to analyze the derivative, or the slope of the tangent line, at different points along this curve. So let's say we analyze the derivative, or the slope of the tangent line, at this point here. So you'll notice that the tangent line has already been drawn for us. So the derivative at this point here would be some positive number because this tangent line has positive slope. And in fact, anywhere over here off to the left, if I were to have picked another point and drawn a tangent line, that location is going to correspond to a tangent line with a positive slope. So that means that the derivative there will be a positive value. Up here at the maximum of this particular function, if I were to draw a tangent line, that tangent line would be horizontal as shown here. And horizontal lines have slope 0. So the derivative would be the value 0. And then anywhere over here off to the right of that maximum value, you'll notice if we draw a tangent line like the one at this point of tangency here, is going to have a negative slope. So the derivative at any location over here at any x value is going to be some negative number. Now what I want you to remember is that now we can find the derivative as a function. And if we can find the derivative as a function, we can graph that function. And so the reason we're analyzing the slope at these different points is because it's going to help us go from the graph of f of x to a sketch of the graph of f prime of x, the derivative function. So what I just said about the slopes of the lines at different points, we're going to summarize in the results below. So at a point x equals a on f of x, if the tangent line has positive slope, so at x equals a, then the derivative f prime of a is going to be a positive value and is going to be located above the x-axis on the graph of f prime of x. If the tangent line on f of x at x equals a has a negative slope, then the derivative at that point, so f prime of a, is going to be a negative value and is going to be located below the x-axis on the graph of f prime of x. And then finally, if the tangent line has slope 0, so it is horizontal on the original graph, then the derivative at that point, f prime of a, is 0. So on the graph of the derivative, it's going to be on the x-axis. So we're going to use this information to help us sketch the graph of f prime of x given the graph of f of x. Alright, so we want to find derivatives graphically given f of x. So this function here is my function f of x, and although I said we are going to be dealing with curves, it's easiest to start out with lines. So this here is my graph of f of x, and what I want to draw is the graph of f prime of x. So f of x is some function, and f prime of x is going to be some function as well. And since f of x is defined for values between, let's see, -6 it looks like, and 8, what I'm going to do is I'm going to draw myself an xy coordinate plane from -6 to -8. So this is just going to be a little rough sketch here. So 2, 4, 6, 8. -2, -4, and -6. Alright, so over here on the graph of f of x, all the way from, let's say that this function does keep going on forever over here. So from -infinity all the way up to 0, but not including 0, I am this linear function here that I can find exactly. It's the function -x. So this linear function right here, -x, has slope -1. So for any value from -infinity all the way up to 0, the derivative is always going to be -1. So on the derivative graph over here, the derivative graph anywhere from -infinity all the way up to 0 is going to be -1. So I'm going to draw my graph over here in blue. So from -infinity all the way up to 1, the derivative is always -1. So if I read this derivative function and I ask you, well, what's the derivative of the original function f at -4? You go to this function and you say, well, it's going to be -1. In fact, for any value to the left of 0, the derivative, or the slope of the tangent line, or in this case just the slope of the line, is -1. Well, let's analyze what's going on exactly at 0. At 0, I have this point of discontinuity, right? I have a removable point of discontinuity. And if a function is discontinuous, it cannot be differentiable. So there's no derivative at the x value of 0. So over here, right here along the y-axis at an x value of 0, I have to make sure that there is no derivative value. So I have to be undefined on the graph of the derivative. So now I can keep going. What about between 0 and 2? Between 0 and 2, this original function is the linear function x. So I can see it has rise over run of 1, so up 1 over 1. So I have the line x, and the derivative of x is just 1, the slope of the line. So this is 1x. So between 0 and 2, I need to be up at a y value of 1. So I'm going to go ahead and draw that as a horizontal line. So I have to be 1 between 0 and 2. And again, at 0, I have to be undefined, so I have to have this open circle there. And at 2, you'll notice that I'm not defined there, so I can't be continuous there. So also at 2, I'm going to have an open circle. And if you notice even closer, between 2 and 3, there are no function values at all. There are no function values. So between 2 all the way up to 3, I cannot be continuous because there's no limit from the left over here and there's no function values in the middle. So from 2 to 3, if I'm not continuous or even defined, I can't have a derivative at those locations. So from 2 to 3, there's going to be a gap. There's not going to be anything there. So if there's no values, there's no limits, there's no continuity, that means there's no derivative. So I have to just skip all the values from 2 to 3, and that includes at 3. So there can't be a derivative right here at 3, right? There's not even a left part to the function. But picking up from 3 onward, let's say this goes all the way to infinity, this is a horizontal line. So this is the horizontal line at 1, so this is the function, y equals 1 from 3 to infinity, and the derivative of a constant function is 0. So from 3 onward, right, so I should have been careful, I shouldn't put the circle up here, the circle should actually be down here, because from 3 onward, I have a derivative that is going to be 0. It's going to be on the x-axis. So this graph here represents my derivative at any point. So in other words, let's imagine that we were not given this function over here. I've never seen this before in my life, but I've been given this function here, f of x, and I'm asked questions about f, the original function. So I'm asked about its derivative. So what is f prime of 1/2? So assuming I don't even know what f looks like, but if I know f prime of x, well, 1/2 would be about right here. So if I read this graph that I've drawn, at 1/2, the derivative is 1. So f prime of 1/2 is 1. What about f prime of 6? So at a value of 6, this function is 0. It's this constant piece of the line. So f prime of 6 is 0 along the x-axis. So it's a little bit tricky, but if we break it down piece by piece and we remember that the derivative is the slope of the tangent line, what I've drawn here, f prime of x, is the slopes of the tangent line, or the lines of this original piecewise function. Alright, so let's take a look at another example. So I have another piecewise function here, and I'm going to go ahead and draw myself an xy plane so that I can draw the derivative of this piecewise function. So this is the function f of x, and we'll go ahead and say that down here it continues on forever, but that it does stop right here at 2. So over here I need to stop at 2, and then I will go ahead and mark up a bunch of values over here, but it is going to go on forever. And here's 0 and 1. Alright, so let's go ahead and start over here where we have this piecewise function and where this piece is linear. So this linear function, if I were to try to draw f prime of x, well, this linear function goes from negative infinity up to 1, so I know that's where I'm going to have to stop right now. And I'm going to draw a line that represents the slope of this line. So I'm going to draw a constant line at the slope of this linear function here. So if I pick a point on this line and I try to determine rise over run, so this point here, this is -1. So here I'm at -3, -1. I'm going to go up 1, and I'm going to go over 1 to get to the point. So this line has slope 1. So up 1, over 1. So from negative infinity, way over here, up to this x value of 1, that's when I stop having a slope of 1. So 1 on the y-axis, I'm going to have this horizontal line at 1 all the way up until this value here at -1, where there's this sharp turn happening. There's a corner. And at a corner, I have a place of non-differentiability. So on the graph of the derivative, there's going to have to be an open circle there. Alright, so now let's go ahead and analyze what's happening between -1 and 0. Between -1 and 0, if I think about drawing a tangent line, because I no longer have a linear function, so I can't say that for every point between -1 and 0, the derivative is always a particular number. But what I can say is that if I draw a bunch of tangent lines, so little tiny tangent lines at different points, what I know about the slopes of each of those lines is that the slope is negative. So what that means is that on the graph of f prime of x, negative values happen down here, right? Happen below the x-axis. So between -1 and 0, so right here, I know that I'm going to need to be below the x-axis. Whoops. So let me erase just the little red part. So I know between -1 and 0, I'm going to have to be below the x-axis. Alright, really close to -1, if I think about drawing a tangent line, that tangent line is going to have a pretty steep negative slope. So let's say it goes, let's say down 3 and right 1. So it has a slope of -3. So right at -1, or really, really close to -1, it has a slope at -3. So remember, we're drawing a sketch. So what's happening then is I move closer to 0, the slope of that line, so I'll kind of remove it. I have this steep slope, and then not so steep, and then a little flatter. And so you can see that the slopes are going to be getting closer and closer to horizontal lines. So the slopes are going to be -3, but then this one might be, down 2 over 1. So this one might be -2. That one was -3, then -1. And it's going to get closer and closer to 0 as I approach 0, because right at 0, I would have a perfectly horizontal tangent line. So at 0 on the derivative, I would be on the x-axis. But from -1 to 0, my values are pretty steep and negative, so -3, and then they end up getting closer to 0. So I can sketch this graph to look something like this. So, first they're -3, then they're getting closer to -2, -1. Ultimately, they're going towards 0. And then picking up at 0 again, up to 2, if we analyze what's happening to the slope, so let's try a different color. Let's try black. So right after 0, I'm going to have a not so steep slope. And as I continue to move closer to 2, the slopes are getting bigger and bigger. So this slope might have been, let's say, 1/2, and then 1, and then 2, and then 5. So these values are getting more positive. So if at first, right here, I'd be 1/2, and then 1, and then at 2, I go all the way up to, we said, 5. So now my slope of the line, my slopes of tangent lines are getting bigger, and they're positive, so I need to be above the x-axis. But right at 5, I made a mistake. Or sorry, right at 2, I made a mistake, because at this point here, I don't have a limit from the left and a limit from the right, so I can't be continuous. If I'm discontinuous, I'm non-differentiable, so I needed to end that at an open circle. And then this would continue left forever if this went down forever, so this would be a sketch of my derivative of this function. Now, again, the points here are vague, so I just chose 5 and I chose -3, but again, it's just a sketch of the graph. So as long as, if you choose -3, as long as your values are getting closer to 0 as you move from left to right, from -1 to 0, then your sketch is accurate. Alright, so now we have one more example. Let's go ahead and start this time off to the right where I have a linear function. So again, here's my f of x, just to label everything. Here's my f prime of x that I'm trying to draw. Starting at 1, from 1 to 3, and we'll say that this goes on and on forever. So 1, 2, 3. Starting at 1, well, at 1, I have this jump discontinuity, so I cannot be differentiable, so I'm going to have a hole at 1. But from 1 on, I have a linear function, so the derivative is going to be the slope of this line. Well, here on this function, we're actually given the line. It's 6 minus x. So that means that the slope of this line is -1. So from 1 to infinity, the derivative is -1. So the derivative graph is going to be down here. At 1, it's no derivative, so I have to be undefined. And then all the way to infinity, I'm going to be the value -1. So now, here's where I have to do a little bit of a sketch because now I have a curve. Well, let's mark the one value we're sure of. Right here at 0, I'm going to have a horizontal tangent line. So at 0, a horizontal tangent line means that the slope is 0. So at 0, I'm going to mark the point 0 on the graph of the derivative. And then I have to interpret what's happening between 0 and 1, and then from negative infinity to 0. So from 0 to 1, let me go ahead and erase this little horizontal line so we can sort of interpret it. So right to the right of 0, if I were to draw a little tiny tangent line, it's going to have a slope of something like, again approximating, 1/8. Not a very steep slope. And as I continue to move along, I'm going to have steeper and steeper slopes. So maybe 1/4, and then 1/2, and then 1. So what I'm saying is that right before I get to 1, I had a slope of 1. So right before I get to the x value of 1, I would have a slope of 1. But right at 1, we agreed I cannot have a point on the graph of the derivative. It has to be undefined. And then starting at 0, it's a small number like 1/8, and then 1/4, and then 1/2. So if I connect that as a line, and again, it's just a sketch, then I'm going to have that my derivative graph between 0 and 1 looks like this line, where the slopes are getting bigger. They're all positive because, again, if we drew little tangent lines, each of these lines has positive slope. And then over here, off to the left, if I were to think about the different tangent lines, so way over here, if I drew a tangent line, that's a pretty steep slope. And then as I continue to move along, my slopes are getting less and less steep, so they're getting flatter. In fact, they're getting closer and closer to being horizontal, where horizontal lines have slope 0. So they start out to be big negative values. So each of these lines has negative slope. So we'd go down and to the right, down and to the right. So this would be some negative slope, like, I don't know, again, we're making up values here, but we'll go ahead and say -6, and then maybe -4, and then -3, -2, -1, -1/2, -1/4. So these values are below the x-axis on the graph of the derivative. Negative values, again, live down here. So let's go to -6. So that's where we said was maybe at about -3. So again, just in our sketch. So we had -6, and then, -3, and -2, -1. So it's like this linear function down here where the values are getting more and more negative because the slopes are getting steeper and steeper. So if I continue this curve, I would get a very, very steep slope where the line would start to look vertical. Of course, it would never get vertical, but it would start to look vertical. So this is going to be a sketch of my derivative graph. So again, if I were to ask you for f prime of -3, so tell me on the original function f of x about the slope of the tangent line at -3. I could look at this graph and say, well, here's -3. I have to go to my derivative where it's close to -6. So what that means is that on the original function, the slope of the tangent line was about -6. So that's how we read the graph of the derivative. But more importantly, how we'd go from a sketch of the original function and reading its slopes to sketching the graph of the derivative.